let's see if we can figure out the acceleration due to gravity. So we're concentrating on this equation right there, that the distance that an object is going to fall is equal to 1/2 times the acceleration due to gravity times time squared. And so we're going to try to figure that out. And what I'm going to use is I've tried doing this in class many times, and I've had people using stopwatches and figured get a lot of people using stopwatches, get an average time for an object to fall of 2 meters or 1.5 meters, whatever it happened to be. And we should come out pretty close. And it turns out that doesn't really work particularly well in class. And what I've noticed is that for times that take under 1/2 second, people using stopwatches becomes incredibly inaccurate. And I've gotten accelerations due to gravity as high as 25 meters per second squared, when it should be closer to 9.8 meters per second squared. And so what I'm going to try to do is use the photo gate. That's the photo gate right there. And the photo gate right there. Try to use a photo gate and to see if we can actually figure it out. Now the object I'm going to drop is basically it's a ruler. Now you might say, well, it's 12 inches. We can figure out the exact length, but it's actually there's a little bit of a bit on the tips right here, and I want to use metric. And so it is, having done the measurement of the tips there, of the little edge pieces, as well as what's marked on here, this is 31.1 centimeters long. And so I am going to now use this. I'm going to drop it, and we're going to try to figure out how long it's going to take for it to fall. Now, a couple things here is when it's falling, we want it to fall as quick as possible. If it starts falling and it starts to rotate like this as it's falling, well, imagine my finger is the sensor right here. As it's falling, well, it's not going to go the full length. The other issue is that as it's falling, if it starts leaning away, then it's also not going to measure the full length. So we want it to fall as like this, as close as possible, to straight down. We don't want it rotating one way or the other. And so we're going to try to actually reproduce that. Let's see, step out of the way. Try to get this as good as possible. So I'm going to be using the PhotoGate with the LabQuest 2. This is a relatively new device for us, and so we're going to see how well this one goes. And so I want the initial velocity to be 0, because that's what the equation is. I want to get it close. And let's try that one again, because I think I've got to be careful as it's falling. It started tilting away as we're doing it. And this is part of the problem with doing some of these experiments. Plus, I wasn't actually timing that time. I forgot to click it the second time. I want to get it close. And we have somewhat of time. It started falling and it started tilting at the same time. I got 0.24829 seconds. So 0.24829 seconds. And so when I work this out mathematically, what I'm plugging into here is the distance it's falling is 0.311 meters, is equal to 1/2 times g times 0.24829 seconds squared. Now let's see how well that shows up. So my initial equation, the one at the bottom, the displacement or distance, since it's going in one direction, so we can use them interchangeably here. The distance is 1/2 times the acceleration times time squared. And so this is the distance right here, times 1/2 times g times the acceleration. And there's a little squared there's a squared written there, even though you can't necessarily see it. So what I'm going to do is, first thing, I'm going to do 1/2 times that squared. So I'm using my calculator. Feel free to do this the long way if you need to. 0.24829 squared. Divide that by 2. And so my equation becomes 0.311 is equal to 0.030824 G. And so when I do the 1/2 times the time squared, I get this number right here. And G right there is not grams. G stands for the acceleration due to gravity, the same G is right there. So if I want to solve for G, well, I have to divide both sides by the coefficient. 0.030824, 0.030824. And so I'm dividing both sides by the coefficient here of G. So on the right-hand side here, those are going to cancel out, and all I'm going to be left with is G. So all I have to do is do this divided by that, and 0.311 divided by that, and I get, for my acceleration due to gravity doing it this way, 10.09 meters per second squared. 10.09 meters per second squared. Well, that is, not the ideal result, but it's a whole lot closer than I've been getting before. So 10.09 meters per second squared versus 9.8 meters per second squared. We'll see how well that shows up. So now dealing 10.09 meters per second squared is the answer that I got right now. 9.8 is the accepted answer. So because there is an accepted answer here, that is rounded off to two significant figures. Since there is an accepted answer, I can do a percent error. And so I take my initial number, I subtract 9.8 from it, and then I divide by 9.8. And I end up with just shy of 3% error. Oh. The number of labs that I have done where 20% error, we're lucky to get 20% error. Here we're under 3% error. So, and I have it videotaped. Now, part of doing science here is we would probably do it several times and make sure, or try to get as perfect a result as possible. I don't have a whole lot of spotters here. At the moment, I'm doing the experiment to know if the thing is tilting one way or the other. And so there it is. And so rejoice, as always, in that which is physics, and especially rejoice in errors under 5%.